And we begin to get the firing from that SA node. The SA node these are my atria. These are my ventricle. Don't leave my class saying anything else. All right? Put this picture into the file cabinet in the brain so it can be pulled out when you get into your programs. Now, my SA node, right here. My AV node, right here. My bundle of His, right here, that branches, moves up this side, moves up that side, right? Okay? So, when that SA node fires, it's got to fire to over here, it's got to fire to there, to my AV node. So, SA node fires. Now think about the time frame that I just wanted us to think about. One cycle per second. It reaches the AV node in 50 milliseconds. I don't know what milli is, to tell you the truth. I just know it's quick. But it's a delay. It's a delay from the SA node to the AV node. Why? Huh? What? Huh? What? So that we don't have them contracting and relaxing at the same time. Why? Huh? What wouldn't go anywhere? Blood. Because I got to allow for what? I have to allow for blood filling atria, flowing to the ventricles, and being pushed out. Now, look at this. It's the signal slows down through the AV node. Well, now wait a minute. I'm giving us a 1 second time frame. All right, I've already had it take 50 milliseconds to get to my AV node, and now you got to tell me that there's a delay from the AV node to my bundle of His? Yeah, there is. So now we've got a delay of about 100 milliseconds. Milli means what? Huh? Milli. Thousandths. Okay? Now, I can't even do that kind of time. Well, I can't do math in my head, so I can't do that kind of time in my head. Okay? So now, I've got a delay from here to here, and it's telling me why. Because I had the blood come into the atria, that blood needs to move to my ventricles. So I've got to have some time for that to occur. And then, once I get to the AV node, I've got to make it to my bundle of His, okay, the AV bundle. I like bundle of His because that's what I learned. okay? And then I got to make sure it travels all the way down, all the way back up. So, what we're going to see, ventricular myocardium. What part is that? My ventricles. Do you remember how they were thick with the muscle? Okay, that cardiac muscle. So, these are thick with that cardiac muscle. The entire amount that you saw around those ventricles depolarizes and contracts almost in unison. Both sides. The papillary muscles, now where were they? They were inside the chambers, okay, extending from you guys remember the papillary muscles? The little huge sausage-looking ridges? Okay? Huge sausage-looking. Huge sausage. Thank you. That was my next question. She was ahead of me. So now, I've had a delay from the SA node to the AV node to the bundle of His along the Purkinje fibers. Now I've had a delay at the papillary muscles. Why? If the papillary muscles are connected to the chordae tendineae are attached to what, table 3? That's table 4. All right, but table 4, to my valves. My bicuspid, my tricuspid. What's that helping control? My flow of blood. So think about this series of events that just took place. This series of events, delay, 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 but we're talking milliseconds, okay? Blood fill, blood flow, blood fill, push. Isn't that kind of cool? All of this taking place. So, ventricular systole. Contraction, all right, ventricular contraction. It progresses up from the apex of the heart. This is the apex, this is the base. All right, it's reversed to what we normally think about. Then, because of the arrangement of the cells, it does this number. Okay, I'm going to try to get that on video. It goes, it twists upwards and then releases, like wringing out a top. That's one cycle. Isn't that cool? Amazing. Oh, there it was, Kay. Now, the cardiocytes, what part of the heart am I referring to now? Do what, table 2? The actual cell. The actual cardiac cell. They have a stable resting potential. The SA node didn't, but the actual working cell, and that's what I kind of want to point out. The actual working cell, which is that cardiac muscle cell, minus 90 millivolts, they depolarize only when stimulated. That's pretty cool. There are 3 phases. Once they depolarize, oh, I erased my chart. But you remember how it goes up like this and back down? Okay? You always have a plateau. Then we get repolarization, recovery. All right? Sodium is important, once again, rushes in, causes that cardiac cell to depolarize, making it more positive. It peaks at plus 30. So if we look at our chart, now this is the actual working cell, the actual cardiac cell. So if we're at minus 90 and it begins to move up, move up, move up, when it gets to positive 30, that's where it peaks. At that point, we are going to have to move into our repolarization. Now, in the heart, we have what's termed a plateau phase. So, roughly, if something plateaus, doesn't it normally do something like that? Did we see that in skeletal muscle or the nerve cell? So, we have a plateau that lasts about 200 to 250 milliseconds. The reason that we need that plateau is at the time of contraction, when this heart contracts, we need to make sure that we've got the expulsion of the blood. That means either going to the lungs, the pulmonary circuit, or going to the systemic circuit. And the one going to the systemic circuit is going to be under a lot of pressure. So the plateau phase allows for that. Now, look what happens here. What ion are we seeing be important here? Calcium. Calcium becomes important to the heart because of the structure of those cells. Once again, do you guys remember anything else in that sentence right there? Was there a term? The troponin. Where do you remember hearing troponin? The skeletal muscle. The troponin and tropomyosin. Okay? So once again, a similar structure because this is skeletal. This is. How did I lose my brain? I totally lost it. This is muscle tissue. Oh man, I totally had the brain go dead on that one. Okay? It is muscle tissue. There were 3 types: skeletal, smooth, cardiac. And so far, they've all had this little complex, these little fibers, these little structures that have to be worked on to make them contract. And this time, we're dependent on the calcium for helping make that contraction occur. Now, once we have that plateau phase and the blood gets ejected, repolarization will occur. Repolarization means that I'm going to go from my positive, move back towards my negative, because the one thing that I have to make sure happens with these cardiac cells is that they are going to recover after they have depolarized. Now, do you guys remember a refractory period from the muscle and the nerve tissue as we repolarize? Okay, so this refractory period, it's much longer than what we see in skeletal muscle. The recovery, this refractory, this returning back to the resting potential to make it do the contraction again. In skeletal muscle, that's only about 1 to 2 milliseconds. In heart, we've got about 250 milliseconds. We have to make sure these cells recover completely. Do you remember in skeletal muscle, if it continued to receive an impulse, it would continue to contract. Contraction would get stronger and stronger and stronger until it reached tetany. Okay? And tetany would be the sustained contraction of the muscle. We cannot have that happen in the heart. The heart cannot handle a sustained contraction of these cardiac cells. I mean, I don't even know if that would be interesting. Just saying. So, if that were to occur, we'd stop that pumping action. And like I've said, I don't know about you guys, I kind of like that action occurring. All right, but that's just